Alrighty, so the next sorting algorithm on our agenda is bubble sort here. If you've seen any sorting algorithms before, you've probably seen bubble sort. Like it's sort of like the simplest one here that like everybody kind of learns as like baby's first sorting algorithm here. So bubble sort is based on a sort of like a simple like little operation that we could do that we could call a compare and swap. So the idea is we're just going to grab an adjacent pair of elements in our sequence, so sequence I and sequence I plus 1. And if they are out of order, right, if the ith element is larger than the element to its right here, then we swap them like that. So like, that doesn't like fix the entire sequence, obviously, but it makes these two a little bit better there, right? If we find an element x that is greater than y, we can improve the universe a little bit there by just swapping them around and putting y first and x later there like that. One thing I'll sort of mention here, we're not going to use this, but notice that this would actually work if you did more than plus 1, right? Like if you did like plus 2 and sequence plus 2 like that, this would still be valid, right? If you sort of like compare a thing to its next door neighbor 3 doors down and you're like, hey, these are out of order, let's swap them. That would still be a valid like transformation to do. We're not going to take advantage of that at all there, but it's something to sort of bear in mind here that like, plus 1, plus 2, plus k, any value greater than or equal to 1 would actually work in this case here. So some things to notice here, right? So we can do a compare and swap anywhere between indexes 0 and this is a less than, that makes it look like a less than or equal to, less than n minus 1. In other words, the last index where we can do this is n minus 2. We can't do it at n minus 1 because then when we do the plus 1, we would be looking at index n, and that's beyond the end of our sequence. So like the last element doesn't have a neighbor that comes after it to compare it to there. Compare and swap is what's called idempotent. I'm not sure if I'm pronouncing that correctly there, but that basically means you can do it over and over at the same index and nothing changes, right? It might change something the first time, but then after that, nothing is going to sort of change there. So that means like it's basically safe to just sort of like hit our sequence with compare and swaps over and over and over, and they'll never make things worse. They either make things better or they leave things the same there like that. So that suggests a simple but like really, really inefficient sorting algorithm. So let's just pick a random index like that right there, and then do a compare and swap there. And then we'll do a check to see if the sequence is sorted yet. And if it is, we're done. Sweet, we get to stop. And if not, we go back to step 1 here. Checking to see if the sequence is sorted, that takes O of n time. We have to loop over the whole sequence to sort of do that there like that, right? So our best case runtime for this would be O of n. Like if the sequence is already sorted, we pick a random spot to do a compare and swap. It doesn't change anything because everything's already in order. And then we check to see if the sequence is sorted, and we say, oh, it's sorted, and we stop there. The worst case runtime, though, is big O of infinity. Because if we're really randomly picking indexes, there's no guarantee that we will actually pick every index. Like we might just get super unlucky and pick the same index over and over and over and over and over and never even look at the rest of the sequence there. So obviously this is like a silly sort of thing here, but it's just the idea is like you could sort by just like sort of hitting your sequence with the compare and swap hammer, just like over and over and over there. But let's see if we can do better. So instead of picking elements at random, right, we're going to iterate the compare and swap in a well-defined order. So we're going to start at index 0 and then go basically all the way to the end there like that. So let's do that on this sequence here, right? So we compare -9 and 2, and -9 is less than 2, so no swap. We compare 2 and 6, 2 is less than 6, so no swap. We compare 6 and 3, 6 is greater than 3, these are out of order, so we swap. 6 is greater than 5, so we swap. 6 is greater than 1, so we swap. So when we're done, this is what my sequence looks like here. The 6 sort of got dragged all the way to the end of the sequence there like that. So 6 moved to the end because it is the largest value that we started that there, right? In that comparison where I do sequence I greater than sequence I plus 1, right? 6 is always going to be greater than whatever comes after it here. So we're always going to sort of swap 6 up there like that. So the effect of running a compare and swap from left to right is to basically find the largest value and drag it or bubble it up to the end of the sequence here. This isn't quite a, like, what goes here kind of sort where we're like, oh, we're finding the largest thing and we're putting it at the end there like that. Because that's not all we're doing. Like, we're swapping other things, like things other than 6 moved around while we were sort of processing this here. If we do it again, right, if we run another pass of the compare and swap here, it will swap the 5 with the 1 and giving me the second largest position sort of in that second to last position there like that. So if we run n passes, not infinity passes, but n passes, all the elements will be put into their correct positions. So that leads to this like really simple 4-line implementation of bubble sort here. So this inner part here is what we had from the previous slide. That's the part that says, okay, just do compare and swaps from beginning to end. And then the outer loop just says, do that n times. Right? Just compare and swap, and then compare and swap, and compare and swap, and compare and swap, and do that n many times. Now, one optimization is to notice that, like, when I is 1, there's no point in comparing against the sort of like the last value there like that, right? So we could like sort of like skip the last value and then skip the last 2 values and then skip the last 3 values. So we can modify the end point of the inner loop here so that it's like not looking at the values that are already sorted. So that this kind of like pulls back from the end of the sequence in the inner loop there as we're sort of putting things, like things get locked into place there like that. So that's a little optimization we can make. That doesn't change the big O of this thing here. So the original big O is basically like a whole n squared, like that. This new version is like this, right? So it's like an n squared over 2. But in big O terms, that's exactly the same as that there, right? But it is like, twice as fast in sort of real world usage there. Hey, yeah, this just works it out, right? The original version is n squared minus n. This one is n minus 1 over 2, which is what we saw from selection sort, right? So it's the same kind of a thing there like that. Unlike selection sort, the swap is inside of an if. So that means that we might not do any swaps. If the sequence is already sorted, we won't do any swaps here. But the downside is we can do up to n squared many swaps in the worst case here. We could do lots and lots of swaps in a bubble sort there like that, right? So as we've written this, bubble sort runs in n squared worst case time. It's in place, right? We don't make a copy of the vector there like that. It is not adaptive. There's no breaks or returns inside of either of the loops that would let us like get out early. So it just always runs in n squared time. But it is stable because we only ever swap things that are right next to each other. We don't do like long distance swaps like in a selection sort here. So that makes this a stable sorting there like that. We're not quite done yet though. Like we can make this adaptive with a little bit of optimization. So let's look at this situation here, right? So let's say that I have a setup like this, right? So I've already sort of done 2 compare and swaps and placed the 5 and the 6 here like that. So now I'm going to sort of like my J loop is going to stop when it gets to this point, when it gets to 3, because there's no point in looking at the 5 and the 6. I know that those are already sorted. So we compare -9 to 1. Those are in order, no swap. Compare the 1 and the 2. Those are in order, no swap. Compare the 2 and the 3. Those are in order, no swap. So I'm done with no swaps. So what does the fact that I did no swaps in this part of the array mean? It means that section is sorted, right? It means that -9 is less than 1, 1 is less than 2, 2 is less than 3. So if I know that this section is sorted and I know that this section is sorted, that means the whole thing has to be sorted. So if I do a pass where we don't do any swaps, I can just return after that. I don't need to sort of keep running the outer loop there. If if I do no swaps, that means the whole thing is sorted and we're done. So to do that, we're just going to add a bool variable here to basically keep track of whether or not I do any swaps. When I do a swap, we'll set that to true. And if I get all the way to the end down here and it's still false, right? Not did swap just means is did swap equal to false, then we can just return. We get to sort of quit early there like that. That improves our best case runtime to O of n if the sequence is already sorted. If the sequence is already sorted, the J loop will go all the way through, but not do any swaps. Did swap will be false, and we'll immediately take the return to exit there like that. So we'll do one pass of the J loop and then be done. So one thing to notice is that if our bubble sort passes move like forward, then large elements move quickly, right? Like big things move towards the end fast, but small elements take longer to get dragged back towards the beginning, right? In a single pass, big things will move a long range towards the end, but small things will only move one step at a time towards the beginning there like that right there. Because of that, large elements are sometimes called rabbits because they move fast, and small elements are called turtles. So turtles are a bit of a problem because they take a long time to get to their correct positions. So a variation on bubble sort is called a cocktail shaker sort. And it's bubble sort where basically we alternate directions. So the first direction goes that way, and then the next pass goes that way, and then the next one goes that way. So that way, what is a turtle switches from big, small, big, small, big, small at each pass there like that. Another variation is called a comb sort here. And this is why I mentioned that the compare and swap will work with any k that is greater than or equal to 1. So in a comb sort, you start by doing compare and swaps with things that are really far apart, and then move the k closer and closer to 1 there like that. So that way, you start out moving turtles long distances and then move down to the point where they're moving sort of shorter and shorter distances like that. So those are a couple of variations that you can build on a bubble sort there like that. So just to sum up, bubble sort runs in O of n squared time. In the worst case, it's in place, it's adaptive, which means the best case is O of n, and it is stable. Bubble sort's usually faster than selection sort, but it's not like the best. Insertion sort, which we're going to look at next, is better than it here. Bubble sort is useful in situations where you don't really need everything to be perfectly sorted. You just need it, kind of sorted. So if you do a couple of passes of bubble sort, it will get more sorted each time there. So maybe you will have a limited amount of time in which you can do your sorting. You're I only have 2 nanoseconds here. So if you do just one pass of a bubble sort, or even not even a whole pass, right? Just pick 3 elements at random, compare and swap them. Each sort of thing you do makes the thing closer to being sorted, even if it is never actually fully sorted. There's some situations where it's you don't need the thing to be completely sorted, but stuff runs faster the closer it is to being completely sorted there. So that's sometimes a place where bubble sort is useful. All right, next up is insertion sort. So if you want to move on to that one, feel free, or don't. I'm not your boss.